This is not stressful at all. But it's really nice to be back here. This used to be my first conference talk ever in 2016, so I'm really, really happy to be back here at JSConf Budapest. Thank you all for coming. Yeah. And Tejas already asked the question, who has any clue what Jose is about? And I think I see one or two hands. It's a bit difficult, but that's very good because it means that you'll learn at least one thing today. I'm not going to spoil what it is yet because we're going to work our way up to Jose. But it is somewhat related to cryptography. And don't be scared. The most difficult part of this talk is, for me at least, pronouncing cryptography. You'll hear me struggle with it the whole time. But let's get started. We only have half an hour. So let me quickly introduce myself. My name is Sam Bellen. I'm a developer advocate engineer at Auth0. We have a booth outside if you want to learn more, or if you have any questions afterwards. I'm a Google developer expert. And if you want to find me on the internet, just look for Sam Bellen. I'm a developer. I'm a JavaScript developer, so it only makes sense to myself that I'm NPM installable. So if you're on npx /about me, download half of the internet. Wait a few seconds. You'll find all of my social links and links to my current and past presentations. If you'd like to follow along now or after this talk or anytime in the future, these slides are available and will always be available at jose.sambega.tech. Open them on your phone, just pay attention to me, whatever you prefer. But I have to start with a few disclaimers because this is a cryptography talk. And the first one is, I will simplify certain things in order to try to explain them in an easier way. Cryptography gets complicated really fast, but we're only going to stay on the surface level of this. And second, don't reinvent the wheel. When you're dealing with something cryptography, use one of the existing libraries. They're made by experts, by professionals who knows what they're doing. Please use what's out there already, and don't try to write your own unless you really know what you're doing. Okay, so in this talk, we're going to have a quick summary of hashing and keyed hashing, signing, digital signatures, encryption, and lastly, we're going to explain what this Jose thing is all about. But let's dive straight into it. So we start with hashing. And a hashing algorithm is a mathematical algorithm that maps data of an arbitrary size to a bit string of a fixed size. A lot of fancy words for just saying, no matter how much input you put into this algorithm, the output will always be the same size, and that size is defined by the algorithm. The initial data is often called the message, and the outcome is called a hash or a message digest. So if I reference to a hash or a message digest, that's what comes out of a hashing algorithm. And it's a one-way function, which means you can put something in it, you'll get your hash, but you will never be able, or you should never be able to reverse that hash back to the original message. It's a one-way function. If you go through it, you can reverse whatever happened in that algorithm. So if we look at a little example, we have three different inputs. Dog, doggo, the quick brown fox jumps over the lazy dog. All three have a different length. They're longer words, they're a sentence. But the output of this algorithm, in this case SHA-256, will have a 256-bit outcome. And that's one of the characteristics of a hash. The output will always be of a fixed bit length, no matter how big the input. It's a one-way function, so you see that the errors go one way. You should never be able to reverse them. And some common algorithms are MD5, SHA-1, 2, 3, NTLM, and so forth and so forth. If you've been doing stuff on the internet, you might have used MD5 in the past. We don't use it that often anymore because there's some security implications, but it's still around. These days we usually use one of the SHAs to do hashing on the internet. So we've seen hashing, a quick overview of what hashing is. One-way function, always fixed length output, can't reverse it. Keyed hashing is just an extra bit on top of regular hashing. So everything we just learned about hashing is still true for keyed hashing, but we're just going to add a little bit extra. So keyed hashes lets you validate the integrity and authenticity of the content of the hash. So how can you do this? How can we validate the integrity, the fact that nobody tried to tamper with whatever content has been hashed? Well, in combination with just the hashing algorithm, it is also going to use a secret key. You can also call this a password or something similar, but it's a secret key on top of a hashing algorithm. So same example, dog, doggo, quick brown fox, but instead of running them through a regular SHA-256 algorithm, we're running them through a keyed hashing algorithm, in this case HMAC SHA-256, so it still uses SHA-256, but adds HMAC on top of that, and together with the inputs we also have a secret, and if we change that secret, the output will also change. So the output is dependent on not only the input, but also the added secret. This means that we can validate the input. We don't have to know the exact input of the hash, but if we know the secret and the the input, we can validate that the hashes are what we expect them to be, because a hash for an input is always going to be the same for the same input. So if we know the key, we know the input, we can say that for certainty, nothing has changed to the input. So it lets us validate the integrity of data in certain instances. And some of the keyed hashing algorithms are HMAC-SHA 256, 384, 512. These are just the bit lengths of the output, but HMAC-SHA is the most commonly used keyed hashing algorithm. I'm going really fast because I have a lot of things to say, but if you have questions, please come up to me afterwards at the Auth0 booth. And some example use cases. When you store passwords, you don't store them in plain text. Please don't store them in plain text. You usually do a lot of things with them. You might salt them, but you probably also use a hashing algorithm or a keyed hashing algorithm to store them in your databases. But you can also do things like identifying files, cache busting, database indexes, and even things in blockchain use hashes. Cool. That was a real short overview of hashes and keyed hashes. Let's move on to the next step, digital signatures or signing. And digital signatures offer all properties that keyed hashes do. So anything that was true for a keyed hash is still true for a digital signature, but they also offer this one very difficult to pronounce thing called cryptographic non-repudiation. And if you look this up on Wikipedia, it tells you non-repudiation refers to a situation where a statement's author cannot successfully dispute its authorship or the validity of an associated contract. Clear, right? What it means is basically this. Cryptographic non-repudiation can prove whoever created the signature. Because we added that little piece on top of it, the cryptographic non-repudiation, we should be able to prove who created the signature. With a keyed hash, anybody that has access to the secret can create a keyed hash. With a cryptographic signature, only a certain person or party should be able to create them in their own name. And the way we do this is using public key cryptography or asymmetric cryptography. So the same thing. They use two different things, one to create something and one to validate something. And to create signatures, to create a signature, the signer, the person that wants to create the signature, is going to create a signature using their private key. And a private key is something that you link to yourself, that you keep secret to yourself, that you don't share with anybody ever. You're going to use that private key to generate your signature, and then you can share that signature with whoever needs to have your digital signature. And they can ask for your public key, and based on that public key, they can validate that the signature is still valid or not, that the content that you tried to sign has not been tampered with, and so forth. But you're only sharing your public key. You never share your private key. And we use a private key to create a signature, and we use a public key to validate a signature. And this basically allows us to do this cryptographic non-repudiation thing that I just talked about. We own the public key. We can confirm that this digital signature has been made by our public key, so they can prove that I made that signature. A signing algorithm is usually a collection of 3 different algorithms. It's something that creates a public and private key pair, which are mathematically linked, something that uses the private key to create a signature, and something that uses the public key to verify a signature. So if we look at the same example as before, a bit simplified, we still have an input. It's still a one-way function, but instead of adding our shared secret, we are now using our private key to create the signature, which will give us an output. Usually this is based on a hash as well, so it's usually also with a fixed length of output. And if we want to validate the signature, we'll need the original input, we'll need the signature, and we'll need the public key that has been linked to the private key that created the signature. And if we have all those 3 pieces of data, which should be public data, we can validate that nothing in the original input has been tampered with, that it is what we expect it to be, that the digital signature is valid or not. So use the public key to validate, the private key to generate a signature. And some signing algorithms, the most commonly used ones, there's a whole bunch of them, but there's a few families. Rsa is the most common one, then you have elliptic curve, and you also have Edwards curve. I'm not going to go into details. If you'd like to talk details, again, come find me in the booth, but we don't have time for this. And some common use cases, Json Web Tokens. If you used Json Web Tokens before, they're usually signed. Sometimes they use a keyed hash for the signature, but most of the time it's recommended to use a digital signing algorithm. And if you want to sign a document online, usually you run that document through a signing algorithm and you create a digital signature as well. So there's a few example use cases. So we can move on to the next and the last part of our introduction to cryptography, encryption. And when encrypting data, we cannot only ensure that the integrity and authenticity is what we want it to be, what we expect it to be, like with signatures and like with keyed hashing, but the data will also stay secret for outsider. Anybody that should not be able to read the data should not be able to read the data. With signatures, the data would be public. With encrypted data, that encrypted data is encrypted for anybody who does not know how to decrypt that data. And you either need a private key, a secret key, or a password, depending on which kind of algorithm you're using. But you can use any of these to encrypt and decrypt data. The output of an encryption algorithm is often called a cipher. When I say cipher, I mean what comes out of an encryption algorithm or what goes into a decryption algorithm. So there's two kinds of encryption. You have symmetric and you have asymmetric. Symmetric is the most simple one. And we use these often for very big pieces of data. If we have to encrypt a lot of data at once, things like a whole file system, your whole hard drive, all your network traffic on your Wi-Fi databases, we usually use a symmetric algorithm just because they're a bit easier to compute, they're a bit faster to compute, they're easier or better to deal with large pieces of data. And the same example, if you'd like to encrypt the quick brown fox, we run it through the encryption algorithm together with a shared secret or a password, and we get our cipher or encrypted message. We can then decrypt, so this is not a one-way function, this is a two-way function. You can decrypt that cipher back if you also know the shared secret. And it's good to know that with a symmetrical algorithm, you use a shared secret to both encrypt and decrypt the data. It's a bit more simple, that's why we use it for simple in terms of cryptography. That's why we use it with large pieces of data, but you use the same shared secret or password to do both the encrypting and decrypting. Which is different from asymmetrical encryption, where you first are going to send, ask the sender, somebody that wants to encrypt the data, for their public key, and a public key you can share, so anybody can share their public key with you. And you're then going to use that public key to encrypt the message. This is a different mindset from digital signatures, where you use the private key to create the signature and the public key to validate. With encryption, it's the other way around, at least mentally. You ask somebody's public key to encrypt the message, and then they can use their private key, which they keep to themselves, to decrypt this. This means that nobody except whoever owns that private key can decrypt the message, which means that the contents of that message would stay secret for the whole world except whoever owns that private key, which is great. That's why encryption is invented. So same example, but instead of using one shared secret, we use a public key to encrypt it, and we use a private key to decrypt the message. Asymmetric encryption, some use cases, TLS, VPN, SSH, there's a lot of use cases, but anytime when you're not using with a big piece of data or you want more security, you often use an asymmetrical algorithm. And some of these are the ones listed on this slide. RSA OAP twice for some reason, I don't know why I did that, but yep. So let's look at a little detailed example of RSA and encryption before we move on to the actual subject, Jose. The first thing we need to do when encrypting something with an asymmetrical algorithm like RSA is generate a public and private key pair. And when you do this, cryptography is often based on very large prime numbers. And when I speak about very large prime numbers, do I mean a million? Do I mean a billion? I mean something like this, where this would be a million, this would be a billion, and I have no idea how to pronounce or name the actual number on screen. But you're dealing with numbers that have 150, 300 digits, a lot of digits, very, very big prime numbers that are really hard to compute. And because they're really hard to compute, that's what makes it so secure to do cryptography with them. So, if you want to generate a public and private key for RSA, we're first going to generate two very large prime numbers. 61 and 53 are not large, but for the sake of this demo, I'm choosing small ones. In reality, they're going to be very large numbers. And then you're going to generate a lambda, which is just a lambda function that you throw in the first and second prime number. So you have these three values, and you're going to keep these values secret somewhere in memory. But you're going to use those three values to generate the public key and the private key. That way, they are somehow mathematically linked. And the public key is going to contain the modulus, n, which is the first prime number times the second, and it's also going to contain the public exponent, which is a co-prime of that lambda value we calculated earlier. And then the private key is also going to contain that modulus, but instead of the public exponent, it's containing the private exponent, which is whatever you see in that mathematical function at the bottom of the screen. But because they use those three values we calculated in the yellow box at the top, they are mathematically linked, and once we generated those two keys, we can forget about the prime numbers and the lambda value. We don't need them anymore. We only need the data, the numbers inside of our public and private key. So, using the public key to encrypt data is as simple as having some input, 1, 2, 3, 4, it's a nice number. We run it through that algorithm in the middle of the yellow box and plug in the n, the modulus, and the public exponent values. And if we do so, we get another number, 2183. Let's remember this one because we are going to decrypt this later. But usually we don't deal with numbers, we deal with any other file types. So you might have to do a bit of file type conversion. But under the hood, whenever you encrypt something, you're always going to be doing a mathematical algorithm, some mathematical calculations. So any type you put into an encryption algorithm is going to convert it to numbers first, and then do the encryption, and then maybe convert it back to something that you expect it to be. So we got a cipher, 218 something. Now we need to decrypt it again to be able to get to the original data, which was 1234. So we do that. We take this 2183, plug it into the algorithm in the yellow box, which is the Rsa Decryption Algorithm, together with the modulus and the private exponent found in a private key. And if all works out, and I've done my math right, we should end up with the original message, which in this case was 1234. So it's just a bunch of mathematics under the hood, and because you are basing both keys, the public key and the private key, on a bunch of common numbers, so suprime numbers and that lambda, they're mathematically linked. Some very clever mathematicians figured out that they could do it that way, so it works. Again, usually you don't work with numbers, but with something else, so there's a bunch of data conversion going on before and after your encryption and decryption, but under the hood, it's just a mathematical function. Cool. So we have 14 minutes left to go into Jose, which is perfect. If you'd like to know more about RSA, I created this little demo website called rsa.sambega.tech. It's a work in progress, doesn't work in Safari, but if you go to it, you'll see that you can enter a message on the top and enter anything, and it will decrypt this message using RSA. I would also give you a bit of an explanation at the bottom, showing you all the numbers it uses. And as you can see, these are quite big numbers that it uses to do the actual encryption and decryption. And it gives you a nice explanation of how these numbers are used to encrypt and decrypt the data. So if you're interested in this, rsa.sambega.tech, check it out later, or tomorrow, or next year, doesn't really matter. It's always going to be there. Hopefully it will be finished one day soon. So let's move on to Jose. And I've asked this before, who knows Jose? I think I saw one or two hands. I'm not sure because some lights on my face, but I think I saw one or two hands. And Jose stands for JSON Object Signing and Encryption. And these are words we know by now. We all know JSON. Yes, right? Yeah. We all know what an object is. This is a JavaScript conference, so I think most of us know what an object is. And we've seen what signing and encryption is in the previous slides of this talk. So all of these words make somehow sense to us in some kind of way. So Jose is just an acronym for Jose, for JSON Object Signing and Encryption, which is a group of specifications that specifies a lot of things. And the most common one is JSON Web Tokens. Who's used a JSON Web Token before? That's a lot of hands. See? All of you have used Jose before without even realizing that you were using Jose or a specification that is part of the Jose specification. But JSON Web Tokens are not the only specification in the Jose specification. I've been saying specification a lot of times, but there's a bunch of them in there. But first, why JSON? Well, the JSON format is often used for serializing and transmitting structured data over a network connection, which means we use JSON on the internet all the time. It has excellent support in most programming languages, especially in JavaScript, since it came from JavaScript. So we all know how to deal with JSON in JavaScript in most programming languages. So it's an easy, very commonly used language, let's call it. So it specifies a bunch of different specifications. JSON Web somethings. JSON Web Tokens is one that I mentioned before, but there's a bunch of others in there. And the first one is a JSON Web Key. And a JSON Web Key is basically just a JSON representation of a public or private key that you can use on the web. And because a private key is something you keep to yourself, most of the time this is going to be a public key that you can share with others in the form of JSON. So if we look at an example, you see that we have a keys array which can contain more keys, but in this case it just contains one. Tells us it's for an RS-256 algorithm. It's an RSA type of algorithm, tells us a bit more. But it also tells us the N and the E value. And if you've paid attention to how we generated the keys in the RSA example, we created a modulus and a public exponent. The modulus is the N version, the N thingy, and the public exponent is the E thingy. So these are the two numbers that we generated in that example. You will also find them in this RSA key. If you use different algorithms, they will contain different kinds of data, depending on the algorithm. But it's basically just a JSON representation of a public or private key you can use to encrypt, decrypt, verify, sign things on the web. Cool. Next up is a JSON Web Signature. And if you've used JSON Web Tokens before, this might look familiar. It's basically a long string with two dots in the middle, separating three different parts. And if you know how to read these, it's a base64 encoded JSON object dot a base64 encoded JSON object dot a signature. And if we look into the first one, the Jose header, it will tell us what this signature, which algorithm has been used to create the signature, HS256 in this case. The payload is the second part, can be anything valid JSON, so anything that's valid JSON, booleans, numbers, strings, objects, arrays, all valid JSON you can put in there as a base64 encoded string. And lastly, the signature is basically taking that header, taking that payload, running it through whatever signature algorithm you specified in the header. This is the key hashing algorithm, but most of the time you use a signature, a signing algorithm, and you get a signature. So that was really short. You have a header, you have a payload, the actual signed data, and then you generate a signature on that, on those pieces of data, and you get it back as a string, so you can send it easily over the network because it's quite compact as a string. The next part is a JWE, JSON Web Encryption, and this is a little bit more complex because it's not just 3 parts. It usually, or it always, consists out of 5 parts. The first part is familiar. It's again the header, the thing that is going to tell us a bit more information about the actual encrypted cipher that we are currently trying to send in this instance. Next up is the JWE encrypted key. And this is an encrypted key that we need to decrypt first. But once we've decrypted this key, we can use this key to decrypt the actual cipher. So a JWE is encrypted using 2 different kinds of encryption, symmetric and asymmetric. We'll see in a second how this actually works. But the second part is that encrypted key that we need to decrypt first. Then you have the initialization vector and the authentication tag in the end, which we can use to decrypt as well. And the fourth part, the cipher text, is the actual encrypted message that we want to send along as a JWE. It's the actual encrypted message that we want to decrypt. So I mentioned this already, JWEs use 2 kinds of encryption. The content encryption key is usually encrypted with an asymmetrical key. Asymmetrical because the key is relatively short. We know what the size of it, so we're going to use a more secure but a bit more complex algorithm to encrypt that encryption key. And okay, so it's the second part. The cipher is encrypted using a symmetrical algorithm because a cipher can be any piece of data, can be a huge piece of data, and we've seen that we usually use symmetrical algorithms for that. So that's encrypted using a symmetrical algorithm, and that uses the content encryption key in the JWE itself to decrypt. So let's see how we do this. The first thing, we look inside of the Jose header, and it tells us a few things. It tells us which algorithm to use to decrypt the content encryption key. It tells us which algorithm to use to decrypt the cipher. And it also tells us the ID of the private key we need to use to decrypt that content encryption key. So the first thing we need to do is decrypt that content encryption key, the second part of our large string. So we see that we need to use RSA OAP for this content encryption key. We take that library that knows how to deal with that algorithm, pass along the content encryption key, the encrypted content encryption key, together with the private key, of which we'll find the ID in the header as well. And if all things work out well, we get a decrypted content encryption key, which means a content encryption key that we can actually use to decrypt our JWE or cipher in this JWE. So to decrypt the actual cipher, we're going to look in our header again. We see that we have to use the A2256 GCM algorithm here, which is a symmetrical algorithm, and it accepts a few things in this case. The cipher, the actual encrypted message in this JWE, the decrypted content encryption key, so the decrypted key that we decrypted in the previous step, together with the initialization vector, which is the third part, and the authentication tag, which is the fifth part. Sometimes the initialization vector is empty, but that's just an FYI. But if you put them all in to an algorithm or a library that knows how to deal with this algorithm, in the end, you're going to get your decrypted message. So it's a bit more complex. You have to deal with 2 kinds of encryption, at least two different algorithms. You first have to decrypt your content encryption key before you can use that actual key to decrypt the cipher. But if you've done everything right, you have a decrypted message that was sent to you as a big string early on. And it's good to know that both JSON Web Signatures and JSON Web Encryption can be serialized as compact, a string. So for a signature, that's 3 parts, and for the JWE, that's 5 parts. But it's called JSON Object Signing and Encryption, so there should also be a JSON variant of this, otherwise the name wouldn't make much sense. So you can also serialize these as a bunch of JSON. Now, usually when we deal with JSON Web Tokens, JWSs and Es, we serialize them as compact, as a string, just because it's more compact to send over the network. But if you want to deal with the data, and we want to deal with the data in a more readable way, in a more structured way, you can always format them as JSON, and this would be an example of a JWS, where you see the same things. You see the payload, you see the header, you see the signature, so you have all these pieces of data that are in that compact string. but just represented as a JSON object. And this would be a JWE. And again, you see your tag, your initialization, authentication tag, your cipher text, your initialization vector. All the things that are in that big string can also be represented as a piece of JSON if it's easier for you to work like this. So let's move on to the next one, JSON Web Tokens. Well, a JSON Web Token is usually just, or is always just a JWS or JWE serialized as a compact string, so the string version. And 99.999% of the time, it's going to be a JWS in a compact version, but it doesn't have to be. If you want to keep the data inside of your payload secure for the outside world, you can also use a JWE, serialized as compact, the one with the 5 parts, as a JSON Web Token. Most of the time, this is overkill, but if you really are concerned with the security or privacy or whatever in your payload, you can use a JWE for it as well. But most of the time, we use JWS because it's way more simple and easier to use. So, again, we have a JSON Web Token header, and next to the algorithm that has been used to create the signature, or the algorithms that have been used to encrypt and the cipher, it also tells us I'm a JSON Web Token, and sometimes it tells you even a bit more about which kind of JSON Web Token it is. So if we look at a few examples, the first one, an access token. An access token is used to get access to an API, so the payload of a JSON Web Token that is being used as an access token is going to contain some information that's useful to an API. So who issued this? Your authorization server, the subject for which user is this access token, the audience for which API is this access token, and this can be multiple. When it's issued at, when it expires at, some scopes, but all information that is useful for an API to get access to an API. An ID token is another example of JSON Web Tokens, which is specified by the OpenID Connect specification. An ID token contains some information about the identity of somebody that authenticated. So instead of having data that's useful for an API, this is going to contain data that is related to the identity of somebody that authenticated. Things like a nickname or a name or a picture, maybe a subject is a user ID, but again, all data that is related to the identity of somebody that authenticated. And the last example is a DPoP proof. DPoP stands for Demonstrable Proof of Possession, which basically means that you can prove that you own a certain access token. And it's going to contain some information related to that. It's going to contain some JSON Web Token ID for which URL this is supposed to be used, for which method. But depending on the use case of a JSON Web Token, the payload is always going to contain data that is relevant for its use case. So there's no standard payload. There's a bunch of different ways, and anything that's valid JSON and of concern or useful for you, you can put inside of that payload. So let's summarize. Hashing compresses and makes it virtually impossible to get to the real data. It's a one-way function. The output is always going to be a fixed bit length, depending on the algorithm. Keyed hashes do everything that a hash does, but it also protects the integrity of the data because you also need to know the secret key in order to calculate the right keyed hash. Digital signatures allow third parties to verify the validity and origin of data. Just because you use a private key to generate the signature, and anybody that has access to your public key, which is public data, can use a public key to validate that signature. Encryption allows only authorized people to read the data, so you usually either use a password or a secret string and then encrypt and decrypt that, or if you use an asymmetrical algorithm, you use your public key, somebody's public key to encrypt the message, and then they can use their own private key to read the data, which means that nobody else should be able to read or decrypt that piece of data. And Jose is a set of standards based on the JSON that helps us with signatures and encryption on the web. You have two different kinds. You have the compact version, which is the JWS as a string with 3 parts, or as JWE as 5 parts. But you also have a JSON version, which is easier to read and it's easier to work with as a developer. Depending on your use case, you can choose both. Unless you use JSON Web Tokens, then they're always going to be the compact string version because you send them over the network a lot of times. These slides are available and will always be available in some kind of way at jose.sambega.tech, jwt.io if you want to know more about JSON Web Tokens, rsa.sambega.tech if you want to see that RSA little website thingy that I'm building and that I demoed a few slides back. If you want to learn more about SHA-256, it's very, very complex, and somebody built a website that explains SHA-256. There's a lot of things going on, but it's really worth it to take a look at it if you want to understand better how it works. It's way more complex than the RSA example that I gave today, but it's a really cool website. That being said, thank you very much.
Wow.